Welcome everybody, my name is Dr. Majid Diwan, an ECFMG certified doctor from Egypt, and this is my channel where we try to simplify medical concepts, especially for those who are preparing for the USMLEs. So, in our first episode, we're gonna talk about the most hated topic among med students, doctors, and even cats. However, USMLE test makers and professors love it. I don't know what I'm saying at this point. Fortunately, I'm here to simplify it for you. So I'm gonna tell you all you need to know about Krebs Cycle, aka TCA cycle, aka citric acid cycle, highlighting the important points, ignoring the low yield points, and just keeping it straight. So, let's start things off with our big guy here, glucose. Do not worry, we're not here to talk about glucose for today. However, this glucose is gonna give us a product called pyruvate. And this process is called glycolysis. As important as that is, again, we're not gonna talk about glycolysis for today because our main focus is Krebs cycle. Then this pyruvate is gonna give us acetyl-CoA. And here, my friends, I can confidently say that the almighty Krebs cycle is about to start. So, the way I think about Krebs cycle is to imagine a giant wall clock. We have 12 o'clock position, 6 o'clock position, 9 o'clock position, and so on. And then I distribute the components of the cycle. So here at the 12 o'clock position is the first man to show up, a very famous man in the lemonade business, Mr. Citrate. On the opposite side, the 6 o'clock position, we have succinate, which is not as famous as citrate. Now, this divides the clock into two halves. Each side have three components. On the right side, starting from the top, we have the identical twin of citrate, which is isocitrate. Then in the middle we have alpha-ketoglutarate. Then at the bottom we have the brother of succinate, which is succinyl-CoA. Moving on to the left side. Starting from the bottom, here we have fumarate, and then malate, and then oxaloacetate. And the way we get citrate again is that oxaloacetate unites with acetyl-CoA. Can you guess the name of the enzyme that makes citrate? Exactly, it's citrate synthase. Let me just connect them real quick. For this part of the video, we're gonna talk about the important enzymes that you can actually figure out by knowing the substrate before it. For example, here we have isocitrate, then the enzyme here is called isocitrate dehydrogenase. And here we have alpha-ketoglutarate, then the enzyme here is called alpha-ketoglutarate dehydrogenase. This enzyme name is not important, but remember that it gives us something very important, which is GTP. Here we have succinate, so this enzyme is gonna be succinate dehydrogenase, and this enzyme is very unique, and I'll tell you why later. And here we have fumarate, not fumarate dehydrogenase, I don't know why. And here we have malate dehydrogenase, then oxaloacetate, then citrate again. And congrats, you just figured out the whole thing. Now let's see the products of these enzymes in action. So this dehydrogenase enzyme takes out the hydrogen from a substance and puts it somewhere else. This somewhere else can either be NAD or fat. These are the names. So this isocitrate dehydrogenase takes out the hydrogen and gives us NADH plus CO2. By the same logic, alpha-ketoglutarate dehydrogenase gives us NADH plus CO2. Also, malate dehydrogenase gives us NADH. You realize that I just skipped succinate dehydrogenase. because it does not give us NADH. It's the only dehydrogenase that gives us FADH2. So, please remember that FADH2 comes before fumarate. And the enzyme fumarase gives us basically nothing. So now let's count our products. 1 NADH, 2 NADH, 3 NADH. So I have 3 NADH plus 1 FADH2 plus 1 GTP plus 2 CO2. So what if I tell you that every NADH equals 2.5 ATPs and every FADH2 equals 1.5 ATPs and 1 GTP equals 1 ATP. So by simple math, 3 multiplied by 2.5 equals 7.5 ATPs. 1 multiplied by 1.5 equals 1.5 ATPs. And 1 multiplied by 1 just equals 1 ATP. So the sum of all of that would be 10 ATPs. So how many ATPs does one Krebs cycle give us? The answer is 10 ATPs. So here is a tricky question. How many Krebs cycle would I get from one molecule of glucose? And the answer would be 2 cycles. The reason why is 1 molecule of glucose gives us 2 molecules of pyruvate and 2 molecules of acetyl-CoA and subsequently 2 Krebs cycles. But just for the sake of simplification, we just talk about 1 Krebs cycle. Now let's talk about some general ideas. Where does this Krebs cycle occur? It occurs in the mitochondria, the energy generator in our cells. The second question is, what is the rate-limiting enzyme? Meaning the enzyme that if you speed up or slow down, it affects the whole process. Meaning, quote unquote, the boss of Krebs cycle. And the answer is you got it, no reviewer. It is isocitrate dehydrogenase. Please remember that. Another question is, what are alpha-ketoglutarate dehydrogenase cofactors? Meaning it cannot function without them. The answer is vitamin B1, B2, B3, B5, and lipoic acid. Please remember that. Again, vitamin B1, B2, B3, B5, and lipoic acid. So, what are the enzymes that require the same cofactors I just mentioned twice? The 2 enzymes are pyruvate dehydrogenase and branched chain alpha-keto acid dehydrogenase, and do not ask me about that now. The next question is, what are the irreversible enzymes? Meaning they only go in one direction. We have 3 enzymes: citrate synthase, isocitrate dehydrogenase, and alpha-ketoglutarate dehydrogenase. The last question is, why is succinate dehydrogenase such a big deal unique enzyme? First, we mentioned earlier that it's the only one that gives us FADH2. Second, it's part of complex 2 in the electron transport chain, which we're gonna talk about in later episodes because it's just a continuation of Krebs cycle. For the final part of this episode, let's talk about the activators and the inhibitors of Krebs cycle. What are the activators of Krebs cycle? As a general rule of thumb, anything that would represent lack of energy would stimulate this whole process. Because if I don't have enough energy, I need to turn on the generator to get the energy. So things like ADP would stimulate isocitrate dehydrogenase. the boss, remember? By another mechanism, we have calcium, and that calcium stimulates both isocitrate and alpha-ketoglutarate dehydrogenase. Moving on to the inhibitors of Krebs cycle. Again, anything that would represent excess energy would stop this whole process, because if I have too much energy, then there is no need to turn on the generator. So things like ATP and NADH inhibit almost all of the enzymes. Another mechanism is that any excess of any product will inhibit the enzyme making it. It's like the negative feedback mechanism we study in endocrinology. So excess acetyl-CoA would inhibit pyruvate dehydrogenase. Excess citrate would inhibit citrate synthase. Excess succinyl-CoA would inhibit alpha-ketoglutarate dehydrogenase. Again, excess acetyl-CoA would inhibit pyruvate dehydrogenase. Excess citrate would inhibit citrate synthase. Excess succinyl-CoA would inhibit alpha-ketoglutarate dehydrogenase. And that, my friends, concludes our quick recap of Krebs cycle. Please let me know in the comments if you have any questions on this topic or any suggestions on how to improve the content. I would really appreciate your feedback, and also please don't forget to hit that subscribe button below to see our next video, and I'll see you in the next one.